So let's talk about probably the core decision that we made as a company over almost 40 years ago. Over 40 years ago, the founder of Phoenix Controls made a very important decision about how we were going to control. He said we were not going to measure airflow in our valves. And if you talk to anyone in the industry who's familiar with Phoenix Controls, that's the one thing they know about Phoenix Controls. Oh, they don't measure airflow. And it's true. We do not measure airflow in the building with our valves. We control through a different methodology, which we'll talk about in just a minute. But first, we want to talk about why we don't measure airflow. Why did we make that decision almost 40 years ago not to measure airflow through our devices? And the truth of the matter is, airflow measurement is not a good solution for critical spaces. It's a perfectly fine solution for a commercial application, for a classroom, for a retail environment, where the cost of inaccuracy is extremely low. In a commercial building, in a educational building, in a classroom, what's the cost if your VAV box is off by 10 or 15%? Virtually none. If you're recirculating most of the air through the building, if the air is going back to the air handler and 80% or 85% is being recirculated through the building, and the terminal unit's off by 15%, any marginal energy loss or energy loss you have is marginal. Okay? And you're not worried about pressure relationships because there's some kind of critical application going on in the space. So again, there's no real cost to inaccuracy. To the point where most of your customers probably don't have a preventative maintenance program for their terminal units. I feel confident saying that. They go out when something's so broken that it can't be ignored and they fix it, right? But in a critical space, 15% error on a terminal unit is the difference between a room being positively pressurized and negatively pressurized. That has real consequences. If you're a hospital and your surgical suite flips from positively pressurized to negatively pressurized, you've got to shut down that surgical suite and decontaminate it and get it back to positive again. That takes that surgery offline for 12 hours, 14 hours. Here's something you may or may not know. The surgery is the profit center of the hospital. Hospitals make a profit every time they cut someone open. Covers the losses everywhere else in the building. They lose money everywhere else, but they make a profit whenever they cut someone open. They do not want that surgery to be down. Okay? So the cost to inaccuracy in a critical environment is much greater. In a chemistry application, if you're off by 15, 20%, you may be maintaining pressure relationships, but those chemistry environments are single pass systems. Meaning the air that you provide to the lab is 100% outside air. So that air has to not only be pushed through the building, it has to be heated or cooled. It may have to be preheated depending on where you are in the world and what season it is. It may have to be reheated. It may have to be humidified or dehumidified, and all of that costs money. So if you're putting 20% more air through that lab than it requires, that's costing the customer money every single day. So the costs to inaccuracy in a critical environment are far greater than the cost to inaccuracy in a standard HVAC application. And that's why we decided not to measure airflow almost 40 years ago. Because airflow measurement is not accurate as it's done in buildings today. There are severe limitations that affect the accuracy of airflow measurement. Installation of your sensors, the speed of response caused by measurement delay, problems with stability and pressure variation, lack of maintenance, accuracy at low velocities of a pressure sensor, and drift over time are all issues, all factors that will affect the accuracy of a flow measurement device in a critical environment. If you read the ASHRAE fundamentals, so this is not Phoenix saying this is ASHRAE, it says you need 10.5 diameters of straight duct run around a flow sensor in a duct in order to accurately measure laminar flow. Tell me how many times you've seen 10.5 diameters of straight duct run in a building around a flow sensor. You'll see one this afternoon for our test stations. We have 100 diameters of straight duct run leading into our flow station on our factory floors. You won't find it in real buildings. So what's the problem with that? You get turbulence in the airstream caused by the lack of laminar flow, which affects the accuracy of your pressure reading. Okay. Speed of response. Okay. Measuring anything adds delay. If you think about what happens when you raise the sash on a chemical fume hood cabinet, you're changing the demand required. The airflow command has to increase because now you need more air to maintain a safe velocity. Okay. In a pressure-dependent system, a system where we're measuring pressure and then adjusting our control device, say a blade damper in this example. Airflow, the volume that we're exhausting, is a combination of two factors. It's the position of the control device and the pressure in the system. If either one of those things changes, it changes the volume of air we're moving through the system. Well, guys, what happens to the pressure in the system when you open up a 10 square foot hole at one end of it? What's going to happen to the pressure in a closed system when you put a 10 square foot hole at one end of it?
Goes away.
It's going to drop, right? Just when we need more volume, the pressure drops out. So, your DDC controller has to have an accurate pressure sensor. We'll talk about why that's not always the case. It has to be set up by an experienced technician who knows how to properly tune that control. Those folks are very rare in the world of BMS systems. You have to have a fast-acting actuator on your control device. And even if all those things are true under perfect conditions, the fact that you're measuring alone is going to cause a 3 to 6 second delay in response to get to the new, higher, safer airflow. Do you know what some folks say the solution to that is? You tell the occupants in the lab to just raise and lower the sash slowly. Has anyone ever tried to tell a PhD anything? Doesn't really work out the way you might think before you try it. Okay? So measuring anything causes an inherent delay. 3 to 6 seconds built in. To get a stable control in a pressure-dependent system, it's going to take 20 to 30 seconds. Because what's going to happen when you slam that damper open in a pressure-dependent system, you're probably going to overshoot by 20 or 30%. In my experience, that's what you're going to do. And so then by the time you dial into to an accurate flow, again, 20, 30 seconds to get stable control. Under perfect conditions. So measuring anything adds an inherent delay. Has anyone worked in process controls? Hold that thought. Hold that thought, I'll come back to it. Has anyone worked in process controls? All right, my favorite television show to watch is a show called How It's Made, because I'm a huge nerd because I love the process controls. Like I don't care about like when they hand make stuff, that's all really impressive. I want to see like the factories. Well, those are controlled by PLCs, process logic controllers typically. And if they're ever filling up a jar of anything, like a jar of peanut butter or a jar of mayonnaise, you see them, like the jars go down the line, and then like a little tube drops in and fills exactly the right amount of peanut butter or mayonnaise, and the jar keeps going. And it happens so fast, they speed up the frames so you can see it. If you were just going at normal speed, you wouldn't even see it happen. Well, what's happening when they're filling those jars, they're not measuring the volume they're putting into that jar, because that would be too slow. That mayonnaise or peanut butter or whatever it is under a certain amount of pressure. And they know if they open up a valve for a certain amount of time at a certain pressure, they'll get exactly the volume they want into that jar. It's the same principle our valves work off of. Our valves meter airflow instead of measuring them, because measuring adds delay. We'll talk about that in just a bit, but that's That's why you don't measure when you need a rapid speed of response. Measuring anything adds delay. Cleaning issues. I talked about this. Your customers don't clean their dirty stuff. When I teach a class for end user customers, I ask them about their preventative maintenance program, where they go out and they clean all of their dirty flow sensors. And you know what the typical response to that question is? They usually laugh in my face. We don't do that. Why would we do that? This is why you would do that. Because if you're not accurately measuring flow, especially in your exhaust systems. Okay? This picture was taken, this is the exhaust of a hospital operating room. And that is the linens from the operating table. Whenever they change the sheets after each surgery, little pieces of lint get into the airstream and they foul that sensor. Now, tell me how much air you're accurately reading through a sensor that looks like that.
I see one hole on the top right.
There's one hole on the top right, so you're going to get some reading. But that blade damper is going to be almost fully open. Well, it's a surgery. Remember, it's going to be positively pressurized. So now your supply is going to have to be massively overused just to maintain your pressurization, if that's what your exhaust looks like. So as I talked about, surgery is the other profit center of the hospital. If that's what that looks like, eventually they're going to be unable to maintain positive pressurization in that operating suite. So they will eventually have to clean that. Hopefully, they designed it smart enough that that box is in the corridor and not in the operating room itself. Because if it's in the operating room itself, not only are they going to have to take that surgery offline to fix that, they're also going to have to then decontaminate the space. So what that involves is, first of all, you go in, you set up your ladder, you put a little tent around your ladder to capture any material that comes out of the ceiling when you move the tile. You move the tile, hopefully there's something cut into the duct so you can get access to the sensor. If not, you're taking your Sawzall and you're cutting a hole in the duct. You're cleaning that sensor, replacing the hole you put in the duct, patching that up, breaking down your tent, breaking down your ladder, vacuuming up all the dust, and then the environmental health and safety team is going to come in behind you, seal that room, and pump a bunch of poison gas in there to kill any organisms that were dropped into the surgery while you had the ceiling open. And that's not a quick process. So that operating suite is now offline for however long it takes to do that, because you had to maintain the flow sensor. Okay. So yeah, so that's, you're not really getting a whole lot of airflow through something like that. Again, flow sensing is subject to fouling. Things get caught up in the airstream, especially in chemical fume hoods. Grad students like to play the game, hey, what can I get sucked up into the airstream? Pieces of paper, empty Mountain Dew bottles, all sorts of things you find up there. Okay, here's another problem. And I like to tell stories, because I think we learn from stories. I'm going to tell you a story. It's a true story. When I started working in controls, I was hired by Andover Controls. I knew absolutely nothing about building controls. As I said, I was a financial software trainer. They hired me, and they said, we're going to teach you the software. We're going to teach you the lab exercises. Don't worry about the applications. The guys in class understand the applications, and then you'll pick it up as you go. And they were mostly right. But something happened early in my career, like the third time I taught the class. The software had this feature in it, which was revolutionary for the time. You could take in a sensor as an input, a physical input, like a velocity pressure input, and you could put an equation right in the input block to convert it to airflow in CFM. You didn't have to send it out to a separate function to do that. And then you could also put in like a min and max value. So this was a new feature. We had to show this off. This was, cutting edge 20 years ago in building controls. So I would teach the class and I'd say, all right, we're going to take this input. It's a velocity pressure input. It's in inches of water, but we're going to convert it to cubic feet per minute using an equation. And we're going to put a min-max value in there. We're going to put a maximum of 1,000 CFM and a minimum of 200 CFM. And I taught the class like that 2 or 3 times until someone raised their hand one day and said, "Hey, Rob, you're doing it wrong." And I was very confused because I was putting the right stuff in the right places. He said, no, I'm not talking about the software. I'm talking about the application. He said, I would never take a VAV box with a maximum flow of 1,000 CFM and try to turn it down to 200 CFM. I said, oh, okay. Why not? He said, because VAV boxes are very accurate at the high end of the flow, but as you turn them down, they tend to lose accuracy. I said, okay. And I kind of did my trainer trick where I looked around the room to see if people were nodding their heads while he was speaking. So I knew he wasn't lying to me. And it was good. They were nodding their heads. I'm like, okay, so what would you do? And he said, well, I would go down from 1,000 to 500, maybe 400 if I'm being really aggressive. So I changed the way I taught that part of the class. And I forgot about it for years until I came to work for Phoenix Controls and someone showed me this slide and I'm like, oh, that's what he was talking about. What this slide is talking about is the accuracy of the pressure transducer you're using to measure the flow in the duct. And if you use a fairly accurate pressure transducer, one with 1% full-scale accuracy, you can still have a great deal of inaccuracy as you go to lower pressures. So in this example, we have a 10-inch diameter duct and a pressure transducer that goes from 0 to 0.25 inches at a 1% accuracy. So at the high end of the flow, at 1,000 CFM, we're very accurate. The actual velocity pressure in that duct is about 0.2095 inches of water. My transducer error is about 0.0025. That's 1% of the full scale. So my measured velocity pressure is very close, and my measured CFM is also very close. About, can't tell the difference between 1,006 and 1,000 CFM. Functionally, it's the same. But to use that example all those years ago I mistakenly used in class, we go from 1,000 CFM down to 200 CFM. Now the pressure we're trying to measure is much smaller. So the potential error of the pressure transducer is a larger percentage of the total signal. And we could be off by, say, 15% or more. That's not really acceptable in a commercial environment, let alone a critical application. The last example here at 100 CFM, the pressure we're trying to measure is smaller than the rated margin of error of the pressure transducer. So you don't really know what the airflow is. You know it's somewhere between 0 and 150 CFM. This is from a competitive product. This is what they say they are accurate to. They have a pressure range of 0 to 1.5 inches of water, 0 to 374 pascals, and a 1% full-scale margin of error. So at 1,000 CFM in a 10-inch duct, they're pretty darn close. Okay, they're within 4% if you take the full error. But at half the flow, at 500 CFM, according to their own margin of error, with a linearity error of 0.015 inches, they can be off by 13, 14% at 500 CFM. Their own documentation, their own rating. At 200 CFM, they could be off as much as 2/3 of the flow. All of that assumes that those pressure transducers are recalibrated according to the manufacturer's recommended recalibration schedule, so that they don't shift over time. Because the more you turn down a pressure transducer, the more it shifts every year. Drifts over time. That's the other thing I ask your customers. I say, guys, tell me about your preventative maintenance program where you go out and you recalibrate all your pressure transducers in all your buildings according to the manufacturer's recommended preventative maintenance schedule. And again, nobody's doing that. So what's happening over time, that pressure transducer becomes less and less accurate. It drifts from 0 if it's not recalibrated. And they just let it go until it gets so far out of calibration that it can't be ignored anymore, and they go out and fix it. Well, in the meantime, what's happening in that building? You're still trying to maintain your pressure relationships. If you're not doing maintenance, you're not spending money on maintenance, you're spending money on energy because you're not accurately controlling the flow in those spaces. So it's going to cost one or the other. You're going to spend the money to perform preventative maintenance to keep your airflows accurate, or you're going to spend the money on the energy you lose from the inaccuracy of your pressure sensors. So if we sum it all up, lack of straight duct runs, system delay, lack of preventative maintenance, and the accuracy of the pressure transducer, failure to counteract drift over time, we could be off 10%, we could be off 20%, we could be off more than that, depending on how long the system's been in place and how little it's been maintained. So for all of those reasons, all those years ago, Phoenix Controls made a decision that we are not going to measure airflow in our systems. We're going to meter the flow instead. And we'll talk about that flow metering approach when we come back from our first break of the day.